Let's look at some more details of these key variables that we are worried about. Mean sea level pressure, OLR, indicator of convection, and sea surface temperature, which is obviously critical for convection and sea level pressure distribution. This is showing the Indian Ocean sector, Eastern Pacific, and the tropical Atlantic. So we are looking at, the meridional sections are shown here averaged over these longitudinal bands, 30-degree bands, and equator is shown here, and the cross here indicates the location of the equator and eta equal to 0. So you see the eta here crossing that line over there. The gray band with countersigned eta exists in this eta or f is less than 0. So either go from here to here or here to here, you end up with eta or f less than 0, which we will use as a proxy for instabilities that exist that are important for convection. Okay. We are again looking at JJA and DJF. I won't go too much into it, but if you look at the Indian Ocean sector, for example, during the summer months, the northern Indian Ocean here has a slight cooling, but this is averaged over the parts of the Arabian Sea and the Bay of Bengal, so one has to be careful. The Southern Ocean is cooler, strong evaporation from the southeasterly trades that become southwesterly and bring moisture onto land. And if you look at mean sea level pressure, there is a strong cross-equatorial pressure gradient that we'll come back to later on, and OLR is low on the equator and into the subtropics, and then it increases again. But again, because of the averaging, you have to be careful exactly what you are looking at. But you know what this is: the monsoon and the equatorial. There are intraseasonal timescale flip-flops between the equatorial region and the land region, which we will come back to when we do the intraseasonal timescales. During December, January, February, you see that sea surface temperature on the equator is still warm, not as warm as here, but still pretty warm with a broader band. Now eta is somewhat different, but almost the same, going from negative values in the southern hemisphere into the positive values in the northern hemisphere. Mean sea level pressure is much flatter now. The ITCZ is to the south, and you have that great cloud band and so on. The Eastern Pacific has much more of a complicated structure. So you have ITCZ around 10 north, where you have a clear dip in the OLR where there is strong convection, and there is the cross-equatorial pressure gradient. This is in the Eastern Pacific, so equatorial convection is not that strong, and mean sea level pressure. So the OLR is actually high in over the cold tongue region and so on. And in the winter, as the ITCZ moves south, you can see the changes in OLR, and it has gone from this deep minimum at about 220 or 215 watts per meter squared down to about 240 or so. And OLR is positive here on the other side. That should be out of the SPCZ, so it's in the cold tongue, and you don't have much of a so you can see the cold sea surface temperatures there in both seasons. And the Atlantic similarly has the ITCZ here, and then SPCZ is partially captured way down here. Okay, it has a huge diagonal structure. Collectively, we can combine these two figures and think about the equatorial trough, or the minimum mean sea level pressure, convection, minimum in OLR, and the SST maxima appearing to be co-located when there is little or no cross-equatorial pressure gradient. Okay, so they are together. These collocations appear in the Eastern Pacific and Eastern Atlantic during DJF and in the warm pool region of the tropical Western Pacific. Okay, so the equatorial trough, I don't know if I want to go back, but nonetheless you can see DJF. So you have the equatorial trough, the OLR, and the SST all together here in the east. Similarly here in the Atlantic. In the Indian Ocean monsoon regions, there exists a strong cross-equatorial pressure gradient, especially during JJA. Convection is located in the summer hemisphere, but equatorward of the minimum surface temperature. So you don't have maximum temperature is here, and there is convection there, but this is equatorward of this maximum convection. Okay, convection is located. This is important as it means that the location of the ITCZ itself is not responsible for the existence of the broad scale latitudinal pressure gradient. So again, this is a bit of diagnostic. So we are looking at the relation between the two. We are not saying which one determines which one, even though we will continuously continue to add that cross-equatorial pressure gradient is important for driving advection of vorticity and instabilities and hence convection. When CEPG is weak, there appears to be a closer collocation of extrema in convection, SST, and surface pressure. We do note that in the Western Pacific Ocean, where the CEPG is weak and SST is homogeneously warm, there is a minimum convection near the equator. So this is where the idea of Philander and the general claim that warm SSTs drive convection begin to be questionable. There are also papers showing that actually it's located at the gradient of SST, maximum gradient of SST, and not maximum SST. But there are many other issues that we will get into as we go on. This raises a few questions which are important that we'll touch on as we go along. Why do maxima in convection and precipitation reside in a particular part of the near equatorial trough and not always in phase with the SST maximum? So some places it's much closer to the maximum, some places quite shifted from the maximum. Why is the intensity of convection stronger in a region of strong cross-equatorial pressure gradient than where there is a weaker CEPG? So when the cross-equatorial pressure gradient is strong, convection is also strong. Returning to figure 13.1c, which I won't go back to, we note that in JJA, there is a band of off-equator convection extending across the central Pacific Ocean west of 140 west, so central eastern Pacific, but where there is a minimum cross-equatorial pressure gradient. This appears to be at odds with these two points above. So what produces this band of convection? So you have the East Pacific convection that is almost close to the warm SSTs in the Pacific, and as if it's pulled by the Gulf of Mexico warm SST. West Pacific, you have a huge warm pool, that's the Indo-Pacific warm pool, and you have convection on the equator and straddling the equator and moving back and forth and so on. In between, you have this long band of ITCZ where the pressure gradient is actually weak, but it is a coherent structure. What causes it? During JJA, the strongest CEPG can be found in the western Indian Ocean, yet there is little convection in the western and central Arabian Sea. So we will also look at that in a bit more detail as we go along. But Indian Ocean is very different, and we will come back to the monsoon in its full glory in a later chapter. We will only touch on it here in the context of the ITCZ and the related processes like the CEPG and advection of absolute vorticity and SST. Okay?